This is Rob Gray from ASU and PerceptionAction.com. Today on the Perception in Action podcast, my interview with Ragiv Ranganthan, Assistant Professor of Kinesiology at Michigan State University. Hi everyone, welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. In today's episode, my interview with Ragiv Ranganthan. Ragiv received his undergraduate degree in electrical engineering before switching to kinesiology. He received his PhD from Penn State University, working under the supervision of Carl Newell. Ragiv has been conducting lots of interesting work related to many of the topics I've been discussing on the podcast recently. In the interview, we discuss motor synergies and redundancy, the role of movement variability in the development of coordination, and using robot-aided movements for rehabilitation. Hope you enjoy!
Not 10 years ago, I was a child. I was a good boy and you let me go. Now I'm on a talk show. Today my guest is Ragiv Ranganthan, Assistant Professor of Kinesiology at Michigan State University. Thanks for taking some time to talk with me, Ragiv.
Thank you, Rob. It's a pleasure.
To start off with, can you tell us a little bit about your background?
Sure. I sort of started out as an engineer back in India when I sort of started my bachelor's degree. And then around my junior and senior year, I was sort of interested in some of the stuff I was learning in terms of techniques, but sort of wanted to look at human movement from a more I was really interested in sports and biomechanics at that point. So I thought, maybe I should think about using some of these techniques for just understanding human movement. And then that's how I kind of moved into kinesiology. And so then I did a master's degree at the University of Illinois at Urbana-Champaign with Les Carlton, and then moved on to get my PhD at Penn State with Carl Newell. And then I did a postdoc with Sandro Musaivaldi at Rehab Institute of Chicago, and then moved to Michigan State. So it's been a sort of interesting mix of a little bit of the applied side, like the sports and the rehab, but also some of the theoretical work as well.
Yeah, that's a nice mix. I'm sure it helps you too. I think from when you do movement science stuff, having a bit of a technical background, because there's so much to do in it in terms of, movement tracking and whatever technology you want to do. To have the engineering side, I'm sure helps you a lot.
Right. And that's been one of the benefits, is to kind of see sort of both worlds, so to speak, both from the engineering side, but also some from the kinesiology motor learning side as well.
Yeah, no, that's great. And you've had some great people you've worked with as well, sounds like. So to dive right into it, the first topic I wanted to start with today is the motor synergies. And so before we get into your work, can you tell us what those are and how they're involved in coordination?
Sure. Well, sort of the word synergies now in the motor literature has sort of multiple meanings. So maybe it's, like you said, it's better to clarify what people think. So there's, sort of the old idea of, that there are too many degrees of freedom for the nervous system to control. So they have to kind of, sort of group or link these degrees of freedom into sort of units, so to speak. So, instead of controlling, say, 100 different degrees of freedom, you control, 4 or 5 sort of units or synergies. And that's been sort of the most popular definition of synergies for a while. And then I think the other take on synergies, and then I'll talk about both a bit because my work kind of crosses both definitions of synergies. The more recent definition has to do with sort of the classic Bernstein idea of repetition without repetition, right? How do you achieve the same outcome without having to necessarily repeat the same movement pattern? So this idea of stabilizing performance variables or being able to achieve a consistent outcome without having to necessarily repeat the same movement is another definition of a synergy. And one of the things that my sort of early work looked at is the relation between these two levels, right? There's sort of this grouping these degrees of freedom into a unit versus achieving consistent outcomes. And we kind of showed that, these two are sort of not necessarily obligatory, right? You can have one without the other. And the way we kind of showed it is by looking at what people would call compensation, right? Compensation meaning if I'm producing, say, 10 newtons with 2 fingers, if one of my finger produces, say, a little less than usual, what does the other finger do, right? And the idea is if it's linked as a synergy, then the other finger should now increase its force so that they sort of compensate for each other. And that compensation, importantly, is compensation in time, right? So when one changes, the other one almost immediately changes to adjust. And the other definition, the repetition without repetition, is not necessarily in time, right? It's sort of more over repetitions. And so this early work that we did showed that you can have no compensation between the fingers, but still have compensation across trials, so to speak, because you can have on one trial, the 2 fingers are producing, say, a certain level of force, and in another trial, they're producing different levels of force, but still the same total amount. And so we kind of, like I said, that's really what it kind of started off with, was to show that these 2 levels of synergies are not sort of interchangeable, right? They are really different, distinct levels of analysis. And it sort of, and in hindsight, we realized this is sort of a version of Simpson's paradox, right? Where you can have a certain correlation within a trial, but have completely different correlations between trials.
That's a really interesting way to look at it. Yeah, I've been kind of struggling with that myself too, the kind of within and between trial. And I know one of the ways in reading some of your work that you've tried to kind of tease these apart is by looking at how feedback affects kind of synergies. Can you talk a little bit about that?
Yes. So that's the first approach that we took. I mean, we kind of did almost like a simulation just as a proof of principle to show that you can have one without the other. But to sort of really understand how it works in human movement, we then did the same sort of 2-finger force control experiment where we manipulated the level of feedback. So you could either have continuous, precise feedback, or you had some intermittent feedback. So you didn't know exactly what you were doing at all times, but you got feedback every so often. And what we found is that, again, the 2 levels of analysis behave differently depending on whether feedback was available or not. So it sort of, again, pointed to this idea that these are really distinct levels of analysis.
Yeah, no, that's really interesting. And I know you've also used some augmented feedback. Has that kind of any differences between just giving it online versus between the trials? Yeah.
And this sort of work started a little bit from the old the guidance hypothesis idea that you provide too much feedback and you get benefits in performance, but sort of ultimately it is detrimental to learning. And one of the things that I think even in the early work, sort of Schmidt and colleagues had pointed to this idea of what they called maladaptive corrections, right? That if you have feedback sort of too frequently or say continuous feedback, then you were sort of making these corrections too much during the movement, which then prevented the long-term retention. And what we wanted to see is, can we actually capture some of this in a task which has redundancy, right? Because now you have a way to really quantify this strategy independent from task performance. So that really was one of the ways we thought, we could probably look at this guidance hypothesis from the viewpoint of redundancy and synergies. And what we found is that people, again, not only is the overall learning, we replicated that finding, of course, like if you provide too much feedback, then you sort of don't learn. But what we also found in terms of the strategies that people used were different when you learned with continuous or concurrent visual feedback, as opposed to if you just got knowledge of results. And that, again, seemed to kind of suggest that, people used information processing and all those explanations, which I think relate to it. But I think what we added to that picture was actually in terms of movement strategy, having more feedback versus less feedback actually changes how you do the task.
Right. So there's not one fit all solution. It really depends on the context and the conditions. Yeah. No, that's really interesting stuff. And I really like how you're really clear about how you define what you mean by synergy, and I think that really helps to understand it. And the next topic I wanted to jump to is one that I've been kind of getting obsessed with, is the role of kind of movement variability in motor learning. And I know you've done a lot of work on that, but first off, I wanted to ask you, can you tell us a little bit how you've conceptualized kind of good versus bad variability in your work?
Yeah, this is something, again, is sort of like, it is still an obsession for me as well when I look into the literature, because there's just so much, and it's hard to kind of try to find a coherent theme to work on. One of the starting points I had was to kind of look at the literature as to how people use variability in learning, and quickly realized people are not always talking about the same thing, that there's not a single sort of construct that was being captured by variability, and people were using it in sort of slightly different ways. So one of the first things decided to do was to try and kind of capture what are the different ways people use variability in learning. And it kind of fell into broadly three buckets. There's sort of the classic schema work and some of the more sort of structural learning ideas as well, where variability is usually introduced to help facilitate formation of a rule, right? So you instead of just learning one thing, if you learned a variation of those tasks, then it helps you sort of develop the rule, which then becomes critical for generalization, right? So if you now have a novel version of the task, then you're much better than somebody who didn't have that variability during practice. The second bucket was more of sort of inspired, I think, from the dynamical systems view, where, sort of the classic, there's the marble in the well. How do you get the marble from one point of the well to another? And there, the idea is, well, the variability kind of provides, if you will, the shaking the marble effectively to move from one point to the other. And here, the concept of variability is really close to sort of optimizing performance or changing a coordination pattern, right? It's not so much about generalization. It's more about sort of finding the best possible spot to be in. And then the third, more recent view that we just talked about is this idea of variability as providing flexibility, right? So it's not necessarily improved performance or a generalization. It's more about, okay, I'm still essentially doing the same task, but some things have changed. Maybe I have an injury, or maybe there are some environmental things that changed. How do I still achieve the same task goal without repeating the same movement? That's sort of the third view of variability. So this kind of framework that we developed helped us a little bit to kind of understand, sort of like you said, how do you define variability? And I wanted to go back to a term that used this sort of good versus bad, which...
Yeah, it's kind of loaded, isn't it?
Yes. It tends to get interpreted differently, because, the idea is that good is somehow good in all ways. And I don't think it was intended like that. It was sort of just a shorthand, I believe, when it was introduced. But like I said, it sort of sometimes gets mixed up as time goes on. So we generally prefer to use the word, null and task, or sometimes relevant versus not relevant, just to avoid this connotation that something is a good or bad. But I think one sort of key point from that is it's not as simple as good versus bad, right? So typically the good variability refers to the variability that doesn't affect task performance, right? And in some ways it's good because it shows that you're flexible. But again, going back to some of the augmented feedback work that we did, one of the things that happens, for example, when you have concurrent feedback, is you have a relatively more good variability than bad, but it sort of then is detrimental to learning. So, is it really good variability if it's detrimental to ultimate learning? It's kind of hard to know. So it's, that's the reason why we've kind of not used those terms as much.
So, yeah, and I totally agree. Potentially good maybe is a better,
right.
So just to clarify, so in yours, if we do the kind of task-based variability, is variability that kind of moves around your goal, right? So if we had the two fingers, pushes you above or below your goal, whereas null space is kind of variability that doesn't. So if you both, one finger went up 1 Newton, one finger went down, that's kind of null space, right?
Yes.
Yeah, I think that's a really good way to look at it. And so can you tell us, I know you've done a fair number of studies trying to look at this, and you know, like you hinted at, sometimes find its benefit and sometimes it's not. Can you tell us some examples of those?
Yeah, sure. So one of the things we did early on is to sort of take a causal approach to this. So a lot of studies prior to that had studied, you know, how the variability in the null space and task space changes with learning. But one of the things that I wanted to do was to say, okay, you know, let's manipulate this variability and see what happens. And one of the things that we found is that, like I said, the main message was this idea of good and bad variability is, you know, doesn't necessarily work at all time scales, right? There's obviously at the level of performance, you could define that, but there's sometimes a distinction between how it works for performance versus how it sort of impacts, you know, ultimate learning. And one of the studies I wanted to mention was we did this, you know, almost a replication, if you will, of the Bernstein idea, where we had participants aiming for a target. You know, they had to take sort of somewhat of a convoluted path to get to the target, so it was not reaching in a straight line. But we then manipulated whether people could take the same path again and again to hit the target, or if, you know, we used a little obstacle in the middle so that they had to try different paths to get to the same target. So again, this would be the sort of Bernstein idea that the you know, the hammer is not traveling across the same path again and again. And what we showed in learning, for example, is, again, this distinction between practicing with more good variability didn't actually help learning. And we were kind of surprised by that, because we were, you know, almost, you know, going into the experiment, we were thinking this would sort of provide a lot of support for the Bernstein idea. But what we found, it's actually not the case, that, you know, practicing all these different paths actually didn't lead to better learning compared to, again, they were not doing the same path, right? The other group was just, they didn't have any external stimulation to change their paths, but they you know, their variability was smaller, but still they were using slightly different paths from trial to trial. Right. And what I think that led to this realization that we can't really talk about good or bad variability without considering the amount of variability, right? And I think that's something that often gets lost in this debate about, you know, whether this is good or bad. Is it's hard to say whether it's good or bad without knowing how much variability you're introducing. And in a sense, it's even hard to quantify how much, right? How much relative to what? And so a more recent study that we did tried to kind of look at this approach, and where we changed both the amount of variability and whether it was good or bad variability. And what we found is it's the amount that matters a lot more than whether you introduce the variability in the good or bad direction. So if you introduce a little bit of variability, we didn't find a really statistical difference, but, you know, looking at the trend, it was in fact even a little bit better than controls. But if you introduced more, right, more meaning more than, I think it was about 2 times the natural variability, then the performance got a lot worse. This is interesting. I mean, from my viewpoint, because, you know, as a coach or a therapist, you're trying to increase variability in the good or bad directions, but it's oftentimes hard to tell how much variability you're introducing, right? Because, you know, it's much harder to control the amount of variability that people are actually going to use when you change something in the task. But our results show that, you know, the amount of variability is probably as critical as, or if not even more critical than whether it's good or bad variability.
Yeah, no, I think that's a really good point. I know people are starting to make some efforts to, like, some of the work like Damien Farrow and they're doing, Tim Buzzer, trying to quantify variability and yourself as well, rather than just lumping it into random versus blocked or whatever. But I think that's a really important movement. I guess the other thing I know I'm trying to sort this out in my head is trying to whether it's possible to divide up null space kind of variability into different types. So what I've been thinking about are things like a differential learning approach, where basically any type of variability, like standing on your head while you do something, is good. Versus, can we actually pick out null space variability that we think might be related to something in the future, some condition you're going to have to perform? And I know you try to do that in your studies. With your reaching study, you actually try to, because wasn't it the case that people in the actual test part were going to have to perform a movement that they'd never performed before?
We did both. We did both a retention where they had to do the same thing, but also did the transfer test as well. Yeah.
Right. So in theory, what you were doing would be help you handle that condition because you've done so many different other ones than the people that are doing all the same one. Yeah.
Right.
But yeah, I think that's a tricky issue, right? A lot more to do on it. And I guess kind of a connecting thread through the couple things we talked about is this idea of, redundancy or degeneracy, that we have these multiple solutions for the same problem. And I know you've looked at that too, like how well people can exploit that and kind of individual differences in that. Can you tell us a little bit about that work?
Sure. One of the things that I did after going to the Rehab Institute of Chicago was sort of start on this paradigm that Sandro had used before, which is called a body-machine interface. And this is really a neat paradigm, in my view, to address some of the issues we have when doing learning studies, right? I mean, a lot of the learning studies typically already, and this is not a new criticism by any stretch, but they typically use things that you're already pretty good at, right? I mean, so reaching and locomotion and all these tasks are already, pretty well learned by the time you're young adults, which is sort of the bulk of the motor learning studies are. And so it really prevents the study of, what people call the early phase of learning, right? How do you actually acquire the coordination to do it in the first place, and not just like the refinement of something that you can already do. And so what this body-machine interface paradigm basically does is it creates a virtual task where there's no, real intuition, but sort of different movements of the body get mapped on to some external object, like a cursor on a screen. So the one that we used a lot was one where people wore a glove, and we basically mapped finger movements to the motion of a mouse cursor on a screen. And again, the neat thing about this is there's no intuition, right? Up and down don't mean anything in terms of how you move the cursor. So people have to really figure out this task from scratch, right? They have no prior knowledge, so to speak, to depend on. And what we find is a lot of, the things that people in real world motor skills have to do, right? They have to do these exploration. They have to sometimes, ditch one effort and try something completely again. And we see this sort of, what we call the really messy stage of learning. But we can quantify that pretty well. And it happens relatively quickly as opposed to some of the real world skills. And one of the things that we found in those studies is, again, you were asking about how well do we exploit redundancy? So what is this redundancy really used for? And one thing that we found in one of our studies was this idea of minimizing effort, right? So if I use the null space, then I can find solutions that are sort of more comfortable in some sense, which makes it, rather than go to the same spot again and again, I can sort of make use of this redundancy to do the task, but do it with minimal effort. That's one finding that we found. In terms of individual differences, this was more work that I did with Adam King, who was at Penn State at that time, and he developed sort of this interesting task where you had a redundancy, not in the sense of usually of the degrees of freedom, but more of a score that was weighted on speed and accuracy. So you could get the same score, if you went really fast or were less accurate, or whether you were really accurate and you went slower. So this sort of interesting redundancy that he developed, and that showed sort of individual differences. So there were, almost clear clusters that formed depending on whether people chose sort of, I guess it was, I don't know if it was related to personality or whatever, but some people started off just going really fast and then kind of improving their accuracy. Some people went exactly the other way, right? They were really accurate to start with and then improved their speed. And then there was this middle group which kind of did a mixture of both. And I think that this task is really nice because it again sort of helps you understand some of these search strategies that people want to study and look at it in terms of their intrinsic dynamics in some way, right? What do they want to do naturally? And so I think it provides a good window to study that.
Yeah, no, that's really interesting. And I agree, individual differences is something we often overlook in motor control research. And I think that's a nice way to do it. I guess the last topic I wanted to touch on with you is, you've already hinted at a couple of times you're in your own lab now, you're doing some work in the area of rehabilitation. And I saw that you're doing some work in kind of robot aided movements. Can you tell us a little bit about what you're working on there?
Sure. It again, I think sort of goes back to the redundancy idea. And there's been a lot of work, and I think you touched on it in one of your earlier podcasts as well, looking at what do we do with the robot, right? And it's hard to really know what exactly needs to be done. And a lot of the rehab studies, in both in terms of clinical trials and others, have shown some promising results. But I think it's probably fair to say not, sort of where people would like it to be. So one of the things that we're really interested in understanding is what do we do with robotic guidance, especially once you add in the problem of redundancy. And so we've developed this sort of trajectory tracking task. It's almost like, tracing a W on a screen, but it's sort of made up of sinusoids, so it's not sort of sharp straight lines. But one of the things we're trying to do is look at a paradigm that Dietrichson developed, where you now have redundancy in the sense of it's a bimanual task. So you're using both hands. But on the screen, you're controlling only a single cursor. So the cursor is basically an average position of the two hands. And so that creates this redundancy because, your hands can be pretty variable while your cursor can still be in the same spot. And so what we're trying to get at now is to look at, now when we add this redundancy, what should the robot do? And we've got this bimanual robot which can apply sort of haptics independently to both hands. So, you could have one hand guided and one hand not, or both hands equally guided. And we're trying to see in terms of, again, benefiting ultimate learning, what sort of guidance should we provide during training. And again, it sort of relates to another thing that you brought up, is this idea of, how aggressively should we fade the guidance? Because I think it's pretty clear that if you provide guidance all the time, it's probably not going to result in very good learning. But sort of how do we go about reducing this guidance over time is something that we're currently looking at.
Yeah, no, I think that's really interesting. And I agree. I think there's still a lot of potential there for, even though there's kind of mixed results first, I think there's a lot of potential there for improvements and new findings. So I guess the last question I have for you is, can you tell us a little bit about some of your current and planned work you have going on in your lab?
Yeah, so there's a couple of lines of work that I've been trying to advance. One of them has to do with coordination, right? So again, trying to look at what people would call relearning, right? So you can already do a task pretty well, but imagine there is a better solution somewhere. How do we get people to move from a solution that they already know to another solution, which potentially is better, but, they used to have to kind of discard whatever they learned to go to this new spot. And I think this sort of relates to a lot of what people do in real life motor learning, right? Sometimes you acquire this short-term, potentially maladaptive technique, and then, your coach or therapist, whoever it is, has to work with you to kind of teach you the, potentially long-term better solution. So we're trying to look at some of these issues in much more constrained tasks, but basically addressing the issue of if you have multiple solutions that do the exact same thing, how do you get people to move from one solution to another? So we've been exploring haptic guidance is one of the things we've been exploring, but we've also been experimenting with reinforcement feedback, right? So not necessarily provide error in a very precise way, but sort of almost like a good versus bad type of thing, and see how people respond to that kind of feedback in moving from one solution to another. So that's one work we've been looking at. The other work we've been looking at is also trying to address this in a rehabilitation setting. So related to this redundancy problem is basically the problem of what people would call compensatory movements in the rehabilitation world, right? So if you had to reach, typically you would reach, say, just with the arm, but if your arm function was impaired, then you might sort of bend at the trunk and sort of use that redundancy to basically achieve the task. And this has been, well quantified in the literature. And one of the things that we are trying to do is to look at how can we, in a way, address these compensatory movement patterns so that people actually result in, using the arm function rather than rely on this trunk movement. And we've been experimenting with some wearable sensors with some collaborations in engineering, and trying to address that problem of, again, what kind of feedback do we do? How often do we have to provide the feedback, et cetera, to change the movement pattern from one to another.
Well, that's really interesting stuff. And I like how you have kind of this common thread running through all your work. It's really nice, connective. I'm sometimes bad at that myself, going off on strands, but that was really great. Thanks for taking some time to talk with me.
Oh, thank you so much, Rob. Again, greatly appreciate it.
Thanks again for the great discussion, Ragiv. You're doing some great work looking at really interesting questions. You can find out more about him from the links I posted in the show notes. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including an extra monthly episode, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep them coupled.
If tears were liquor